Okay, so just a very quick recap of what we did yesterday. So we introduced this space of systems with a pole of order m, a system of size n by n. So I used the notation capital S syst for it. And we had a notion of equivalence on it, which was the gauge equivalence. So I introduced all that notation. And then the modular, so that group, gauge group, blackboard G sub n, that is a group that's acting on this set. And so we're interested in understanding this quotient, which I call the moduli space of systems. And so kind of a little bit more explicitly, we saw that this set of systems is basically n by n matrices with coefficients in convergent power series. And then we started kind of going case by case. So the first case was no pole at all, so m is 0 or less. And then we saw that because of the existence uniqueness theorem, any such system is equivalent to the trivial system like this. And so that means that the whole moduli space is just a single point represented by this trivial system. So there's not much, nothing else to say about this. And then the next case up was m equal to 1, and we did it kind of in two steps. First, we covered the step of scalar systems, so n equal to 1. And we saw that we could isolate the residue, so n0 was the residue. Isolate the residue, and then all the other higher terms, we could remove them by a gauge transformation always. And so that means any system is equivalent to a standard, to a normal form of this form, where we just have the residue and nothing else. So, and these systems are clearly just parameterized by the choice of the residue, which is a number in C. And so what we see is that the whole moduli space is just isomorphic to a copy of C. And then we tried to perform the same analysis for general rank n systems, and that was slightly more complicated. We had to find gauge transformations, and we had to make kind of additional assumptions in order to find a gauge transformation at each step in the expansion. And so that imposed a condition, simplifying assumption, which I called resonance or non-resonance. So these were the non-resonant systems. And so this cut out an open dense subset in the moduli space of systems. And the result is that the reason this open dense subset is so nice is because every non-resonant system does have a well-defined normal form. You can reduce it to a normal form using gauge transformations. And the normal form is very appealing. It's just you just have a diagonal matrix of the eigenvalues of the residue. So this is just the this is just the diagonalization of your residue. So if you like, this is G0 res G0 inverse. So this is just the diagonal matrix of local exponents of our system. And then the rest can be removed by a gauge transformation. And so that presents this moduli space really as a subset of C to the n, because in order to specify a particular normal form, all I have to do is give you a bunch, n complex numbers. So that's a point in C to the n, and I just need to ensure that these complex numbers satisfy some assumptions. So in particular, that this whole thing has to remain non-resonant, so that the differences are not an integer, and so on. So this cuts out a subset of C to the n given by algebraic equations, infinitely many algebraic equations, but nevertheless algebraic equations. So that proves that this moduli space has the structure of an algebraic variety. It's a subvariety of C to the n. Yeah.
Is there a way to relate systems which have flipped eigenvalues?
Which have what?
Flipped eigenvalues. Is there a permutation group still?
Yeah. So that you could say that this I mean, you could write this down as this is a subset of C to the n. You could write that operation as an automorphism on your variety, and then you can quotient by that automorphism. I'm not saying that the quotient by that automorphism results in something smooth. I'm not talking about smoothness of this variety, but it does remain an algebraic variety.
Okay. So you can like if you wanted you could choose them to be ordered.
Yeah. In fact, what we did in the extension, where I kind of gave an indication of what the rest of the moduli space looks like when I removed this non-resonance assumption, there was this preference to order the eigenvalues by their real parts, which was like this. So indeed, in this case, because part of the non-resonance assumption is that the eigenvalues are distinct, this would be there would be a single order like this. Right. Okay, so any questions about this? Right, okay, so today I want to tackle the next case up, or if you like, the remaining case, which is M is at least 2. And so this means we have a singularity of higher order, and we call these irregular singularities. And we'll see that the behavior of these systems and these gauge equivalence classes in the context of irregular singularities is markedly different. But, so let's try and build up to it. So what this means is we have a system of this form, and just like in the case m equal to 1, it was convenient to separate the leading order part. Here it is convenient to separate all the orders of A up to n minus 1. So we'll write the system like this. So I'll just have a polynomial in Z of degree m minus 1. And then the rest I'll just separate into some B. And so this part, I will sometimes write it as P of nabla. This is called the principal part. So, okay, so once again, let's take up the case, the simple case of scalar systems. So n equals to 1, let's try that. So in this case, I will write the system like this. A naught plus A1, Z. So now these are all scalars. Scalar functions, literally scalars. Minus Z to the M of Z. So this guy, maybe I'll denote by lambda of Z. This is a polynomial now, literally a polynomial in Z of degree M minus 1. And B of Z is some convergent paraseries of Z. And so what I claim is that I can always remove this high order part by gauge transformation. So let's see how this goes. Yeah.
Little n is the size of A, is that right?
Little n is the size of A, yeah. So, so let me define a gauge transformation. So if I integrate B and differentiate and exponentiate it, then so first of all, I'm guaranteed that this is a convergent power series, and moreover, it's a convergent power series with leading term literally equal to 1, so it's an invertible convergent power series. So this is what we call GL1 with coefficients in convergent power series. And then, so then I claim that nabla is the gauge, is gauge equivalent to nabla naught, where nabla naught is just the principal part of nabla. So I think you can see why that would be the case. If I differentiate this, I'll get a copy of B down, and I'm necessarily going to be differentiating with respect to z to the m by z. So I'll get a copy of B down by z to the m. I get precisely this guy. And then there's going to be a G inverse, which will cancel G. We've done this calculation before. Okay, so right, so the conclusion, as before, is that so if I look at systems, the moduli space of systems with an order m pole, so here m is 2 or greater, of rank 1, scalar systems, then this is this moduli space is basically the set of gauge equivalence classes of these normal forms. So yeah, so we can say, you know, lambda z is a polynomial of degree n minus 1. That's the kind of complete description of this moduli space. And so to give any one of these, all you need to do is give me a polynomial of degree m minus 1, and that just means I need to give you m complex numbers. That specifies completely a polynomial. And so therefore, what we find is that this moduli space is just isomorphic to C to the m. And you can think that the isomorphism here is essentially just the principal part. So like you take a rank 1 system, you extract the principal part, you look at the coefficients of the principal part, and that's precisely the coordinatization of your moduli space. Yeah.
Here you assume there's only a pole of order 2?
Yeah.
There can't be like one pole of order 1 and a pole of order 2?
Oh, but so remember, we're only looking very locally, right?
We only look at the closest pole?
We literally zoom in, we pick a pole of interest and we zoom in, and then everything else is completely irrelevant. We don't see any other poles. It's like they're kind of infinitely far away from the point of view of the infinitesimal disk, right? That's not to say that, you know, if I pick a specific system, write down a system, that I'm not saying that it doesn't have any other poles around. It will. Just like, you know, if you write down a convergent power series and then turn that into a holomorphic function, by analytic continuation, you know, it has usually some kind of finite radius of convergence. And the reason it has a finite radius of convergence is because maybe at the boundary of that radius of convergence, there could be a pole or something. So, but just by looking at the convergent power series, it's very difficult to like, it's not, you can't really see that without extensive analysis. And that's exactly what's happening here as well. We study systems extremely locally, so we just see the pole that we're interested in. And there are other poles, but they are irrelevant for our analysis. Any other questions?
So you can't like the principal part is just like you can't get rid of it in any way.
Yeah, the principal part, you can't get rid of it. Let's just do a simple calculation. So like if I have my connection, if I have my system, nabla, which looks like z to the m del z minus lambda of z, right? Suppose I now conjugate it by a gauge transformation, G inverse. So what am I going to get? I am going to get, so the operator will pop out as usual. Now there's going to be a conjugation of lambda, right? And then there is going to be the gauge term, which looks like z to the m d by dz g times g inverse. Is this, yeah? Everyone was okay with this? I did it a bit too quickly. Okay, so the fact of the matter is, lambda is a scalar, g is a scalar, so these commute. So these things just cancel out. So this thing just remains lambda. And this term, well, whatever it is, it's all already at order at least z to the m. So it cannot affect any of the lower order parts. So that's why lambda is completely invariant. Other questions? Okay, so let's think about the general case. So the observation here is that just like we saw for m equal to 1, the leading order path, A0, is gauge equivalent up to conjugation. Gauge invariant. Up to conjugation. But the situation is more complicated because, you know, all these other coefficients in the principal part, A1, A2, you know, they are no longer gauge invariant, simply up to conjugation. So it's more complicated. But A1, and minus 1 are not. So let's do a calculation and see what's happening exactly. So suppose I have some kind of gauge transformation, G, and I'm conjugating my system, nabla. And for simplicity, let me just assume, quite enough, that m equals to 2. It will already reveal all the required phenomena. Right, okay, so let me write this. So as usual, we have the differential operator popping out. Then we have the conjugation of the principal part. Then we have the gauge term, z squared del z g inverse. And then we also have the conjugation of b. And, well, okay, so all I want from this calculation really is to see how G affects the principal part. So I actually, in this calculation, I only care about terms up to the order of Z. So all of these, I'm just going to ignore them. I'm just going to put them into this notation for z squared. Okay, so how are we going to do this calculation? So, you know, in particular, like, I want to try to expand G as a power series of Z to see how the leading term of Z and the subleading term of Z, how they affect the principal part. So there's one kind of concerning thing, which is that I want to expand G as a power series, but I have a negative. How the hell do you compute the inverse of a matrix which is a power series of matrices? So here's a good skill to know. So okay, so here's I'm going to write G. I'm going to write it like this. So what I did, so G0 is just the leading term of G, and I've factored it out from, so by H here I mean power series. Like this. And actually I want to put a minus here, sorry. Yeah, so what I did was I factored out G to the right and put everything else into this power series of H, which I called H. So you know, so what that means is, for example, the leading, so the subleading term G1 in a power series expansion of G is minus H0 G0, for example. The reason I'm doing it like this, you'll see in a minute why this is convenient. But in particular, so I will, you know, I've already said this, I only care about order up to Z. So even in this expansion, I'm going to suppress anything that is of order Z squared or higher. So I will write this furthermore like this. So I will only care about the H0 matrix, G0, and then whatever remains, yeah, I put it into this notation. Does this make sense? So here, just for completeness, G0 is an invertible matrix. All the other matrices, HK, are just n by n matrices. The reason it's convenient to write G like this is because then it is easy to find, to write down the inverse. Just because we remember the, what is the name of it? The geometric series, the formula for the geometric series. Remember that, like, if remember this formula? So this, the thing in bracket here for me is my 1 minus r. And so I'm looking for the inverse of 1 minus r. So I'm kind of looking for 1 over 1 minus r. And so what I have to do is I just need to take, this is my r. And I just need to take a series of powers of r. So that's a very neat trick. So that means G inverse is, so there's G0 inverse goes on the left, and now I'm using this formula. H of Z to the K. And again, now, so let me now use, again, this bit, the fact that I only care about order at most 1. That means, yeah, so I only need this huge series up to the order of z. What I get is z h0, and then there's other stuff that I no longer care about. So if you, if there aren't many things that you wish to take away from this mini course, but maybe inverting power series of matrices could be one of them. It's a lifelong skill. Right, okay, so now I'm going to use this here. So I'm going to continue this equality. So I'm just going to use this formula. So we have z squared dz minus, now we have 1 minus z h0 g0 times a naught times g0 inverse 1 plus z h0 minus g0, minus 1 minus z h0 g0 a1 z g0 inverse 1 plus z h0 and all the higher order stuff. Does this make sense? And in fact, I can make it kind of even more simplification here. There's already a z here. So this term, if I multiply it in, I will get a power of z squared, which will get absorbed into this thing. So I can just ignore this. And the same comment for this term. So really, these brackets here just completely disappear. And so in the end, if you simplify this, the expression you get is like this. I wonder if I can fit it. So z squared dz minus, so the conjugation as we expected of the leading order part, and then I gather everything that is of order z. So we get g0, a0, g0 inverse, h0 minus h0, g0, a0, g0 inverse plus g0, a1, g0 inverse. So that's the expression. So now let me make another simplifying assumption. So I see that, to begin with, I have this G0, A0, G0 inverse, so conjugation of A0, and it keeps reappearing twice in here. And G0 is really up to me to pick. So if, in particular, if I assume that A0 is diagonalizable, the generic assumption, then I can choose G0 simply to be one that diagonalizes A0 to its diagonal matrix of eigenvalues. So let me do that. So assume A0 is, or has distinct eigenvalues. And pick G0 such that this conjugation G naught, A naught, G naught inverse is the diagonal matrix of the eigenvalues, which maybe I'll call lambda naught. So then with this assumption, this expression becomes more legible. So I can now ignore basically all G naughts almost. So what we get is lambda naught minus Z lambda naught H naught minus H naught lambda naught plus G A naught A1 G naught inverse plus. And so now we can clearly see that we have a commutator appearing in this formula. So let me write it. Actually, I want it with a minus. Just introduce an extra minus. So we have G A naught G inverse minus the commutator of H naught and lambda naught plus higher order stuff.
I think you meant A1.
A1, yes, thank you.
G naught.
And G naught. Thank you. Right, okay. Okay, and so kind of very similar to what we did when m equal to 1. At this stage, this is kind of like the second stage or first order in our simplification scheme. We basically want to choose H naught, right, which is part of the definition of G. We want to choose H naught such that that term is as simple as possible. Ideally, we might wish to just like cancel it, just have nothing at order Z. But that is not possible. But something almost as good as possible. So here's a linear algebra fact. Another linear algebra fact, which is very cute and useful for your general livelihood. So let me introduce two more pieces of notation. So remember that little gln, that stands for the vector space of all n by n matrices, n by n complex matrices. So I'll put a little plus as a superscript to mean off diagonal matrices. So it's the it's a sub vector space, in fact, of diagonal matrices. Meaning that they have zeros on the diagonal and stuff everywhere else. So that's a vector subspace. And then complementary to it is the subspace of diagonal matrices, which I'll maybe put 0 superscript. So these are diagonal matrices. And so the fact goes like this. So for any n by n matrix A with distinct eigenvalues, that's the important assumption. the adjoint map, which is basically just commutate the map, which is the commutator with A, known as the adjoint map, denoted usually by little ad sub A. So what does this do? This takes a matrix in GLN and outputs another matrix in GLN, which is the commutator. With A. Okay, so the fact is about this map. So first of all, it's a linear map. This part is easy because this part is just XA minus AX. So we basically did that check. We thought about this yesterday a little bit. We had a very similar looking map. So it's a linear map. But then it has a very important property when you restrict it to the off-diagonal matrices, so which restricts to an isomorphism on the off-diagonal matrices. So if I restrict it to GLN plus, it outputs off-diagonal matrices, and this is a one-to-one thing. Very neat fact.
It's a complement of the diagonal.
So there's no condition on A.
Yeah, there is a condition that it has distinct eigenvalues. That is crucial. If I drop or relax that, then this gets ruined.
You can even have 0 eigenvalue?
Yeah. Yeah, so it's nothing to do with whether or not A is invertible or not. It's really just to do with whether or not it has distinct eigenvalues. Basically, reason being that if it has distinct eigenvalues, so or like you could say, okay, this is a linear map, so I can write down a matrix for this linear map and compute its eigenvalues. That's one way to see whether or not it's invertible or not, or whether or not it is an isomorphism. And the eigenvalues of this map, when you restrict it to the off-diagonal matrices, to this subspace. So on the subspace, the matrix representing this has eigenvalues which are all the differences, distinct differences between the eigenvalues of A. So if I assume that A has distinct eigenvalues, then all the differences will be non-zero. And so that literally shows that all the eigenvalues of this matrix, this linear map, are non-zero numbers. So it has to be invertible. That's more or less it's very neat. Okay, so, and this is going to be very helpful for us here because, of course, here exactly we have the adjoint map where A gets replaced by this diagonal matrix lambda naught, which we have just assumed has distinct eigenvalues. And H naught is our X. That's what we are, that's the adjoint map is applied to H naught. And so what we're looking for, we're trying to find H naught, which can kill as much of this matrix as possible. So this matrix is some, basically arbitrary matrix in GLN, but it has diagonal part and off-diagonal part, right? The diagonal part or the off-diagonal part is something that is exactly this thing is designed for, to kill. So we can literally pick a unique, in fact, H naught that will kill the off-diagonal part of this matrix, and all that will remain is the diagonal part of this. So that's the strategy. So using this fact, therefore, we can say that there exists a unique H naught, a matrix in GLN, an off-diagonal matrix in GLN, such that this commutator is precisely that matrix G naught A1 G naught inverse, the off-diagonal part of it. So by this I just mean the off-diagonal part of this matrix. And so what remains is the diagonal part, and I'll just call that lambda 1. G0, A1, G0 inverse. And so therefore, we get a final simplification, which is to say that this system has been transformed into one where the principal part is just diagonal. So I'll write it like this: lambda naught plus lambda 1z plus lots of junk at high order. So this guy is maybe what I'll call lambda of z. This is a you could say this is a polynomial in diagonal matrices of degree, well, in this case, it's degree 1, which is 2 minus 1, which is n minus 1. Does this make sense?
Yeah. If there's still some leftovers maybe from the fact that there can be G0 matrices preserving the diagonal along the 0.
Sorry, can you read the first one?
Like, is there still something left over from G0?
You mean like the fact that here I'm only giving myself freedom of choosing the off-diagonal part?
No, I mean, like, before you fixed G0 to sort of fix G0 so that you could make A0 to be nice.
Yeah.
There could still be some like leftover freedom in that, like a G0 matrix is fixing lambda 0.
Well, sure. I mean, you know, with this assumption, the assumption that the eigenvalue is distinct, once I fix the diagonal matrix of eigenvalues, then the only freedom is something that would commute with that diagonal matrix. And that's just, those are just scalar matrices. Those are the only things that will commute. Right? Because otherwise you'll have permutations. So yes, I mean, there's always a scalar matrix symmetry. That's always present, no matter what. Just because scalars, yeah, that's really what makes all these things into stacks rather than natural modular spaces. You'll always have to remove. Those are the stabilizers that are always present. Now, if you start relaxing this assumption, then of course the normalizer of whatever it is that you fix the leading order part to be, the normalizer might grow. I don't know if there's any use in using that extra freedom, maybe, but not in general, really. All right. Okay, so let's do a concrete example, very concrete example, and it's going to be the system which I mentioned yesterday as one of the examples. So that's going to be our main player for today. So concrete example. And so I'm looking at this system. This is a system of rank 2 and order 2. It's sort of rather quite innocent looking, because most of the entries are 0. But somehow I love this example because it sort of has got a wealth of phenomena. So this was my A0, and this was my A1. and in this case B is just 0. So there's nothing of higher order. So it looks very innocent. Okay, so what can we observe? So first of all, the leading order part, A0, is already diagonal. So I can just take G0 to be the identity and not worry about it. So A0 is the same thing as lambda naught, and we take G0 to be the identity. And then if I look at, so what is lambda 1 in this kind of normal form for at least for the principal part? So lambda 1 it's supposed to be the diagonal part of A1. But of course the diagonal part of A1 is just 0. So this is the 0 matrix. So in this case, this polynomial, diagonal polynomial, which replaces the principal part, is extremely simple. It's just A0. Okay, so what I want to do, the calculation I want to do is I want to basically show you, when I do this operation, when I go from nabla to one who's, to a nabla 1, whose principal part has this diagonal form using this operation, I want to see what gets left over. So let me write my gauge transformation as I did before, 1 minus z h. So there's no more g naught, and in fact I will get away with h just being a constant matrix, constant off-diagonal matrix. So this is what replaces h, or maybe I should just put h naught for consistency. So this is my h naught. So this guy is of the form h1, h2, like this. So I'm interested in finding what h1 and h2 should be. And so this guy is supposed to satisfying this identity that h naught lambda naught is supposed to be the off-diagonal part of A1, which of course is just all of A1. And so if you literally just compute this, let me skip this calculation. What we find is that you find that h1 needs to be equal to 1 and h2 needs to be equal to 0. And so in that case, G inverse is very simple to calculate. So G inverse is just becomes, it's an infinite power series in Z. In Z and H naught, but notice that H naught is nilpotent. So actually, already the second power of H naught is 0. So this infinite power series terminates at k equal to 1. So this guy is actually just 1 plus Z H naught. Right. So because H naught squared is 0. So that means that if I compute G nabla G inverse, this is like, this now becomes a really simple calculation. It just looks like this. This is my nabla. And then my G inverse, which now is also really, really simple. And so if you work this out, which I did last night, punctuated by fending off attacks from my son. So it follows that nabla 1, which is the gauge transformed version of nabla, becomes z squared del z minus, this is just a naught, and then, so this is the stuff that appears at higher order. So it's like this.
That's a note, but it has a minus sign in the matrix.
Sorry. Thank you. Right, okay, so the conclusion I want to kind of draw from this is that this operation of kind of diagonalizing the principal part seems like a good idea because it sort of simplifies the leading part of the system, which in some sense controls, the majority of the behavior of the system. But ultimately it's somewhat unsatisfactory because this system, this gauge transform system is only marginally simpler, at least in some respects, than the original system, nabla naught.
Can I ask something? Just
Yeah.
When you expand G inverse, you have it as an expansion in H naught.
Yeah.
Is that so? When we were doing it in general, it was just in terms of H of Z. So is there only?
Yeah. So that would be H of Z
Yeah.
here. Sorry, that would be H of Z here, okay?
Yeah.
So you can then expand H of Z, and that would be powers of the power series. So it's complicated.
So is there like a? Okay. Yeah. So is it just that H of Z is just H naught in this case, or is?
In this case, yeah, exactly. In this case, I just took H of Z to be a constant matrix H naught. The reason I got away with this is because m is equal to 2, and so I know that like what we saw from the previous from this calculation, in fact, is that in order to modify the part of the principal part of order Z, all I needed to, the only thing that affects it is H naught.
Yeah. Okay.
Right. All the other higher terms in G, they just get absorbed in here.
Yeah. Okay. Yeah.
So if I'm looking for a gauge transformation in this example, only for the purpose of tinkering with the principal part, then I don't have to. I don't have to worry about other terms. I don't have to include. This is the only part of the gauge transformation that I'm caring about in this example.
So is there implicitly a plus order Z squared, or is it just that it is actually?
Well, let me state this as a lemma, and this should answer your question. So, okay, so the stuff that we did. So I want to kind of now summarize it in a little bit more formal terms. So, okay, let me first of all again introduce one more piece of notation. So cyst with a heart, M, N. So these are going to be all the systems, basically, which are amenable to this trick of diagonalizing the principal part. And all I needed for that was was this kind of assumption that the leading order part of the system, sorry, not this one, that the leading order part of the system has distinct eigenvalues. That was my main tool because I wanted to apply that linear algebra fact. So A naught has distinct eigenvalues. And so this is a subset of all systems. And once again, because the constraint that I'm imposing on my systems is given by just a bunch of algebraic equations, just says that one eigenvalue cannot equal to another eigenvalue. This presents it as an open dense subset. So, in some sense, this subset of these, so to speak, nice or nicer systems, it covers almost all possible systems. Having said that, of course, the complement of this, so the systems which don't satisfy this property, is an extremely complicated, but very, very interesting and exciting subset to study. But it's kind of very high codimension, and it has various stratifications. And all of that is extremely exciting, but we won't talk about it. Was there a hand up? Yeah.
Can you define open dense? So do you mean that by like any system in your big system can be approximated to as some kind of sequence of the system to the heart?
That's one way to think about it. Another way to think about it is that just imagine that this is some kind of big manifold of some dimension, and this is an open subset in it, and the complement is a bunch of submanifolds of lower dimension. So imagine let's say this is a complex plane, so this is a real dimensional manifold of dimension 2, real manifold of dimension 2, and it has, a submanifold, which is a line. And maybe there's another submanifold, and another submanifold, and another submanifold. So this is the picture that you could have in mind, that the complement of all these lines, and there could be strata which are really complicated because they involve intersections of multiple of these strata, and so this would be kind of an even lower dimensional strata. So this is the picture you should have in mind, that the complement of all these lines, that's system hot. And all these lines are exactly the subsets which are defined by, let's say this line is exactly the subset which says, the first eigenvalue is equal to the second eigenvalue. So any system that lands here will not be a nice system because it fails for that reason, that two eigenvalues coincide. But, so the important thing is that they're kind of much lower dimensional strata. And so what I mean by dense is, well, I hope this picture kind of makes it clear. So this is the cartoon. This is the cartoon of this space. Right, okay, so let me state a lemma. So, lemma. Yeah, so if nabla, which let me remind you is of this form, so here by A I mean this polynomial. So if nabla is a nice system, then so there's a few things we can say. So first of all, we can always choose G0, just an ordinary invertible matrix, which diagonalizes the leading order part. And then I look at these conjugates of all the other coefficients of A. And I look at their diagonal parts. So this is the diagonal part. And I introduce lambda of z to be this polynomial with these diagonal parts. So lambda naught, lambda 1z, plus lambda m minus 1 z to the m minus 1. Then the statement of this lemma is that once I fixed G0, there is a unique gauge transformation, in fact a polynomial gauge transformation, G of z of degree m minus 2 such that nabla gets transformed by G into a more or less the standard form. So where nabla 1 is this system with the diagonal principal part. And then all the other junk gets relegated into this B prime sum. For some B prime, which is just some matrix of convergent power series, determined entirely by B and G. B and G not. So it's yeah.
Is there a connection between the capital cyst heart and the lowercase quotient cyst heart that we defined for the resonance systems?
Not quite. Yeah. So they're kind of they're both sort of attempting to identify a subset of systems which are in some sense nice, but the condition of niceness really different. So this is you can see that there is, this shows you very starkly that the behavior between the case of m equal to 1 and m equal to 2 or higher, they are really quite different.
Should that be should that be n minus 1, not n minus 2?
Sorry, just a second.
So this is not the quotient of the little cyst heart.
It's not. Mm-hmm. Yeah. So it is quite different, right? So there is still some kind of condition on the leading part, but it's different in style. It is different in style. Sorry, what were you saying?
Should be n minus 1, not n minus 2 in the sum. If we have a counterexample, because this is 2, 2, so if n minus 2 would be just a k equals 0 term, and we have a...
Yeah, you're right. Mm-hmm.
Perfect, thank you very much.
Yeah. Right. So yeah. So this is it's a type of simplifying result. It's not a fully satisfactory simplification. So what it shows, maybe let me restate this result or explain this result in like one sentence. So what it says is that, so in other words, any system, any nice system is gauge equivalent to a system with a diagonal principal part. So, okay, maybe even more diagrammatically. So if I look at this, at the corresponding moduli space, I can kind of express it a little more explicitly. So it's basically parametrized by such systems where we have a diagonal principal part and then junk. And so just to be specific, so lambda is a polynomial of degree m minus 1, z to the k, and it's diagonal. And lambda naught has distinct, or maybe write it like this, so lambda naught, which is the diagonal matrix lambda 1 through lambda n, these satisfy the condition that lambda I does not equal to lambda j for all ij. And then B is just some arbitrary, whatever, matrix, any. So in some sense, this is a complete description of this moduli space, but it is unsatisfactory because although kind of we now have a very good handle on this principal part, we see that it's essentially a bunch of diagonal matrices, but then this B of Z is just completely kind of wild. It could be it's this entire enormous space. So this does give a kind of a smaller presentation of this moduli space, but it's not. The story is evidently more complicated than what we had when we had m equal to 1. Where we had this kind of very neat description, finite dimensional description, literally finite dimensional description of that moduli space. Here, the description that I'm giving you is infinite dimensional. Okay, so now you could say, well, okay, but isn't like my complaint, isn't it rooted simply in the fact that all I did today was worry about tinkering with the principal part, and I was just moving all the remaining junk into B, and I didn't do anything to B. What if let's just try and kill B to the best of our ability. And so this is where the crux of the problem arises. So let me state this as a theorem. So if I have a system, nabla, and let's say this is a nice system, so let's say I have this system. Consider the, I would like to maybe write down a normal form for this system, and then kind of explain, like we did in the previous case, explain, hopefully maybe have a result like we have this normal form, and any system is gauge equivalent to this normal form. And so the naive, obvious candidate for a normal form here is just this principal part, and then just try to kill everything else. I mean, that's what we had for n equal to 1 as well. We literally were able to get the principal part, and then everything that followed the principal part, we were able to kill it using gauge transformation. So let me think about this related system, z to the m minus lambda of z. So lambda being, obtained from nabla using this lemma. So this is going to be my normal form. So this theorem has two parts. One part is really positive, and the other one is really negative in sentiment. So the first part says that indeed there exists a unique G, which I'll call G hat actually. So this is a power series which starts with the identity matrix. K1. Oh, actually, sorry. Let me make just an additional assumption so that this statement is neater. So, and assume the leading part is already diagonal. Just because I don't want to carry G0 around I just want to set G0 to be the identity. This is always possible to do because we're assuming that the eigenvalues of A0 are distinct, so it's always possible to diagonalize it. So I can just apply a constant gauge transformation G0 from the very start and then proceed. So I'll just make this assumption. Then indeed I have this power series starting with the identity matrix. All these GKs are G-line matrices, such that, indeed, if I apply G hat to my normal form, I get nabla. So this is great stuff. We can always do this, and in fact, there is a unique once I fix the diagonalization of A0, once I fix the diagonalization of A0, the matrix that does everything for me, so puts it in this normal form, exists and it's unique. So that's great. And here comes the huge downside. So this one is kind of really, really important property of, or a really, really important phenomenon that happens in this business. So generically, except in other words, except in some really, really trivial cases, generically, this power series of Z, of matrices, is a divergent series. Meaning it has zero radius of convergence. So in other words, this nice, great-looking power series in Z, which would be the candidate for my gauge transformation, is not a gauge transformation. So G hat does not belong to my gauge group. So what this means let me erase that as well. So what this means is that the two systems, nabla, that I started with, the nice system nabla, and its normal form, nabla not, they are formally gauge equivalent, but not actually gauge equivalent. So So nabla 1 and, sorry, not nabla, nabla not, are formally gauge equivalent, but not analytically. You could say, in more concrete terms, you could say that, you know, if the cool thing about nabla not is that it is genuinely a diagonal system, so I can just solve it on the nose. So finding y naught, which gets killed by nabla not, is very simple. And that means I can define a y hat, which is just g times y naught. And this y hat does get killed by nabla. But this y hat, this is not an analytic solution. It has 0 radius of convergence. So let me maybe try to formalize this a little more. And then we'll take a break and then we'll do an example. So let me introduce this group. So blackboard G, N, but now Z is inside double brackets. So what this is it's just the group GLN with coefficients in the algebra of formal power series. So notice that you know, any convergent power series is in particular a power series, a formal power series. So we have this obvious inclusion. And so that means we have the inclusion of the gauge groups as well. And so if I'm looking at this moduli space of nice systems, this is by definition the quotient of nice systems by our convergent or analytic gauge group. You know, I can try to divide by. I can instead take a bigger gauge group, which is this one, divide by it. So the quotient therefore would be smaller, in the sense that I have a surjective map like this, and well, I could call this, it's some other version of this moduli space, maybe syst hat. So I have a surjective map. And so kind of unfortunately, you know, one way I could sort of try to describe this picture is that this moduli space is in some sense too big. I say it's too big because it's basically, it doesn't allow us to, you know, given a system, it doesn't allow us to extract enough somehow finite information to nail down a nice looking normal form that we can actually work with. All I could do was, you know, settle for having some kind of junky B. So this moduli space is just a little bit too big. But this moduli space is too small. Because although I can nail down a really nice looking normal form, a really easy to work with normal form, I cannot properly relate it to my given system by some kind of analytic gauge transformation. So it's only sort of, it's a partial success. So ideally, therefore, you know, I would maybe like to try and find something in between. And actually, as I was preparing these lectures, I realized that the story, at least told in this way, whatever the moduli space that's supposed to appear in between, it doesn't really appear in the literature as far as I can tell. So, so let's take a break here. Yeah, let's take a break here. And then when we return, we'll do a concrete example and and see how far we get. Right, okay, so we ended with this theorem, which says that, you know, if I have a system of type Mn, even if it's a nice system, then it is possible to put it in normal form. But that comes at a price, which is that the transformation that puts it in normal form is divergent. So here's a concrete example where we can see this phenomenon occurring. So let's return to this system that we've been studying. So so it has a second pole, and it's just got these two terms, and the normal form is well. So the A0 part is always diagonal, so that stays, and the A1 part, the diagonal part of A1 is just the zero matrix. There's nothing else. Okay, and so let's try. You know, so suppose. You know, I look for a gauge transformation, so a 2x2 matrix with entries which I'll call Gij. So suppose this thing is such that it takes number naught to number. So what does that imply? Let's see what that would imply about these coefficients Gij. What kind of conditions must they satisfy? So, okay, so if we literally just write this identity out, this equation out, we get something like this. So there's the conjugation term, and there's the gauge term. Is equal to A0 plus A1 Z. And so that means that maybe I can write it in this form. So I'll multiply by G on the right. And so I get this differential equation for G, which looks like the commutator A0 with G, I think, plus A1 G Z. I think that's what I got. Right, okay, and so if you crank this thing out, then you will find, I'll skip the calculation, but I encourage you to do this. You will find that G has to be, if we, let me say it like this. If we insist that the leading order part of G is the identity, then G must be the form. It just turns out to be an upper triangular matrix with just one entry, which I'll call G. G of Z. And, and this G of Z must satisfy a differential equation. So that differential equation just comes from this differential equation. And the differential equation looks like this. It's Z G prime plus G is equal to Z. So this is kind of a famous equation. It even has a name, or at least I call it that, and some people call it that. It's called the Euler's equation. So I want to now show you some slides. So basically what we've done is we've boiled down our problem. If we are intent on finding a gauge transformation G which puts nabla in a standard form, we must therefore find a holomorphic solution of this equation. So basically this equation is now what I want to study. I want to understand this. Where's the remote control? Here. Ah, thank you.
Sorry, should it be Z squared? You just wrote Z.
It is Z.
Oh, it is just Z, because this is Z.
Z squared. No, that's right, sorry. Yes, thank you. Thank you.
I think you have to change the source.
Nothing up here? The HDMI?
I don't know which remote belongs to which.
When you pressed on that one, it did something here, so maybe.
There we go. Let's see, HDMI.
try HDMI 3.
This is not how I envisioned this.
But I think we can also see pretty well that one from here. So.
See?
Yeah, I saw.
Okay. Okay, so this is the problem I want to solve. So this is the same Euler equation. Now, so let me kind of do it in stages. So I'm just going to formulate this as a problem now. So let's just find all solutions of this Euler equation, and for the moment, let's just restrict our attention to the real line. Just make it simpler. So that's the problem. Let's find all solutions. And just kind of as an aside, you can use some kind of methods from ODEs, like the integrating factor method, to write down the general solution of this. But what I want us to do is I want us to pretend that we don't know this method, and the only method that is available to us is the power series method, which is relevant, of course, because we're sort of trying to kind of construct some kind of power series here. So, so that's our ansatz for solving this equation. It's just a power series in X. So if you do this, so you substitute this ansatz into the equation, you get a recursion, and it's very simple. You get that the first coefficient, the 0th coefficient, why did it dim?
Yeah, because your screen is...
Oh, because, yeah. Right, I better not touch it. Anyway, the leading coefficient is 0, the next coefficient is 1, and all the subsequent ones satisfy this beautiful relation, which you can actually unpackage and repackage into an explicit form, explicit equation for the explicit expression for the coefficients, which is just this alternating k factorial. And so this immediately shows you the fact that this thing is a k factorial, that this power series is not convergent. You use a comparison test or whatever the... So what you obtain as a result is what is called the Euler series. So it's this really nice, beautiful looking power series with integer coefficients. So a little bit of history. Why is it called the Euler series? So I dug up a paper of Euler from 1760 called On Divergent Series, so very appropriate for us. And so in that paper, he was already studying this series exactly. So there it is. You can see that he sets x equal to 1, and that's precisely that series, which he calls the Wallace hypergeometric series. So it's a numerical series, and somehow he was interested in he was studying divergent series, and his question was, is there a way that we can assign some kind of numerical value to a divergent series in a meaningful way? And so this was one of the things that he tackled, which he called the Wallace hypergeometric series. So it's literally our formal power series of x, where I just kind of manually substitute 1 for x. And by the way, over here, this is also why I call it the Euler equation, because here, kind of on another page, he literally is studying the differential equation that this series must satisfy. So here he's got slightly strange notation. but basically you need to multiply this by x squared and divide by dx, and you get precisely our the equation that I wrote down. Okay, so this Wallet hypergeometric series, I'll also return to it because it's kind of fun. Right, okay, so this is the problem that we've got. We've got this ODE that we want to find all solutions on the real line. And we found a solution, which is this power series, the Euler series. It comes with some drawbacks. So first of all, I've already noted that this series is divergent. So it's not a true analytic object. I can't just take a value of x, plug in, and expect a number. So that's not so good. And then there's kind of another, maybe in some sense, an even more worrying problem, which is that, we do know the properties of ODEs, and when we have a linear ODE of order 1, as we have it here, we know that the solutions form a vector space of dimension 1, right? So we would expect, if this power series method were appropriate, we would expect to try and recover a one-dimensional family of solutions. But here we just get just one solution. And you can try, whatever, if you take two times the Euler series, that just won't satisfy the differential equation. So never mind the fact that this solution is divergent, so not a true analytic solution. It's not. It's at best a particular solution. Okay, so in other words, this power series method, which seems like a really good thing to do because it allowed us to write down this beautiful series, it kind of misses almost all the solutions. But let's proceed anyway and see what we get. And the key observation is somewhat left field, and this is basically an observation due to Borel from the late 19th century, early 20th century. And what he noticed is that so this part is slightly crazy, but basically our monomial x, we can rewrite this if I assume that x is positive, then this is a true equality. I can rewrite this x as an improper integral, where I'm just integrating 1 against this, what is known as the Laplace kernel, e to the minus t over x. So you can see that if I'm assuming that x is positive, and I'm integrating t from 0 to infinity, so as t gets very large and positive, and x remains positive, the exponent in this exponential remains large and negative. And so that means this function that we're integrating is kind of having an exponential damping at infinity, and so this integral is well defined. So those of you who have done any bit of kind of physics or proper calculus will recognize that this is the Laplace transform of the constant function 1, and it's similar formula for the monomial t to the k, the Laplace transform of that. You get a monomial x to the k plus 1 with a k factorial coefficient. So these are true equalities when x is positive. So what I want to do is I want to use that equality in our formula for the Euler series. So this is now going to be a hugely controversial slide, as I'm going to do something completely illegal. Okay, so this is our Euler series. So far, so good. And what I am noticing here is that this coefficient, k factorial x to the k plus 1, is exactly the thing that I have in the formula out there. So let me just use this true equality and make a substitution. So far, so good. So far, this is all mathematically nice and good. Here comes, this is where shit hits the fan. Because now I'm going to interchange integration and summation. Of course, this is illegal, but as I like to say, we all have a degree in physics or mathematics, so we've earned the right to break the rules. So that's what we're going to do. So so I've interchanged summation and integration, and I've also rearranged the terms a little bit. So I've combined t to the k with this alternating sign and put it into a sum and made it green to make it extra attractive. And the reason I did that is because hopefully you can recognize what this sum is. This is we've already encountered it today. In fact, this is the geometric series, right? It has a closed. First of all, it's a power series in T, which has a non-zero radius of convergence, right? In stark contrast to the Euler series, this has a non-zero radius of convergence, and moreover, within its disk of convergence, it has a very nice expression as a meromorphic function, right? It's just this wonderful fraction, 1 over 1 plus t. So, I would say this equality is also a little bit iffy because, yeah, exactly. Because I'm sort of here, although this is now a convergent power series, right? So it kind of makes sense analytically to integrate it, but I am integrating it, explicitly over a domain which is strictly larger than its radius of convergence. Some kind of fishy stuff is going on here, right? This one, on the other hand, this expression is perfectly fine. I have a globally defined meromorphic function with a pole at t equal to -1, which is nowhere near the domain of integration, and I'm just integrating that globally defined meromorphic function, and so this is like this equality is perfectly legal. Nothing wrong with that, and this defines for me some kind of holomorphic function of x. As long as x remains positive, this is, maybe I shouldn't call it a holomorphic, but it's an analytic function of x where x is positive. So, like, by hook or by crook, we started with something that basically had no analytic meaning and ended up with something that has a perfectly well-defined analytic meaning. Okay, so this is bad. This was the legal trick. So we went from a formal power series, and somehow, with some kind of trickery, we extracted an analytic function out of it. And a priori, I could replace this with any other analytic function, and you would be none the wiser. But the important thing about this specific analytic function is that it's actually a solution of the Euler equation. It's not just some arbitrary nonsense that I somehow, pulled out of my left shoe. That's not an English expression. No, it's deeply connected to the equation that I'm actually attempting to solve. And there's an even deeper connection, which is that if I take this analytic function, the Euler function of x, and I try to construct its asymptotic power series as x goes to 0 from the right, then the asymptotic series is nothing but the Euler series. So there's this very strong relationship between the formal Euler series that we started with and this Euler function. And so as an aside, in fact, if you did manage to remember the integrating factor method and you got that nice closed form solution, nice closed form expression for your solution, you'll find that relate the Euler this Euler integral that I wrote down to that closed form just by doing this this substitution. So in other words, it is a particular solution that we encountered before, so the trick, this illegal trick that makes this possible, can actually be made mathematically sound. And the key word here is Borel resummation. So what we did here, we started with a formal power series and we applied Borel resummation, which I'm about to explain how that goes. And the output of this operation is a formal, is an analytic function with which has multiple properties. One of them being this relationship with the formal power series that I employed. So let me try to explain this in a little more detail. So this is the calculation. I just repeated the calculation here. And so I want to explain kind of in a very pragmatic way what Borel resummation does. What are the steps involved in Borel resummation? So the first step was this this idea that I started with a formal power series in X, had 0 radius of convergence, and I essentially replaced it with some other power series in T, which was convergent. And the key to this operation, or the key of this sudden appearance of some convergence properties was the fact that this power series, as opposed to this power series, was missing a k factorial in the coefficients. So you could say just mechanically, you could call this operation a Borel transform. And it essentially, what it does is it divides every coefficient by k factorial. There's an invariant way to define what a Borel transform is, but it's okay. We can just stick with this very pragmatic point of view. So this is what I just said. In general, you have a power series in X. Borel transform provides. This should be a phi hat of T. Provides for you another power series, an auxiliary power series in a variable T, where you just well, there's some shift going on, k plus 1, but then you divide by k factorial. So that was the first step. The second step was the tricky one. We recognized that this convergent power series actually converges to a nice-looking analytic function, which was 1 over 1 plus t. And the significance of that was that this analytic function, 1 over 1 plus t, its domain of definition exceeds far beyond the radius of convergence of this power series. So the mathematical words here is that we took a convergent power series and we constructed its analytic continuation. That's what it was. We've analytically continued this holomorphic function from its disk of convergence to the whole complex plane minus a pole at minus 1. And then once we've done that, then the third step is that we've applied to this analytic function, we've applied this improper integral, which is just the Laplace transform. So again, the formula is you just take phi and Laplace transform it. And so the combination of all these three steps is essentially, by definition, what you call the Borel resummation procedure. And the output, so if all the steps work, and you can see that there are multiple things that can go wrong at every step, but if they do work, then the output is an analytic function of x, which has f hat as its asymptotic expansion. Yeah?
Does a Borel transform in general also assume positive x, or was that just the specific one?
Can you say it again? Sorry.
When we did the first step of the previous example, we had to say it only worked for x positive.
Ah, right. No. So this formula, I mean, has nothing to do with positivity of x. Yeah. So it's a very general formula. Right. Okay. So right. So let me just make a few comments. Yeah, the well-definedness of this procedure, depends basically on every step. Nothing going wrong at every step. And I would say that the first step is very simple. It's very mechanical. You just need to ensure that the power series that you get in the end, after dividing by k factorial, is convergent. And so that just places kind of a condition on the type of formal power series we consider. So that's usually, in practice, that's pretty simple to do. The really difficult step, the step that, you know, if you look at any paper that properly discusses Borel summation of some quantity, the 95% of the work in that paper is spent on step 2. Analytic continuation of holomorphic functions is genuinely a very difficult operation, highly non-trivial operation. If you manage to do that, then somehow, you know, taking the Laplace transform is usually also not so difficult. So the fact that, you know, in this example, our power series, this Borel transformed power series, had this very simple expression for its analytic continuation, was a kind of a pure lucky accident, which is why I chose this example. So let me, as a quick aside, let me return to this Wallace hypergeometric series. So now we can again ask the question. You know, we have this divergent numerical series, which is the value of the Euler series at x equal to 1. And so we can ask, what is the value of this? And traditionally, you'd say it doesn't have a value because it doesn't converge. But now we can answer this differently. We can say, well, the Euler series has a Borel resummation to a true analytic function, which is the Euler integral of x. And that analytic function makes perfect sense at x equal to 1. It's a perfectly well-defined function. And so we can evaluate the Euler integral at x equal to 1 and get an actual number. And that's what perhaps we should assign to the Euler series. And so this exists. This is fairly easy to compute. You get this weird number. And if you look at Euler's paper, he actually, by some kind of other completely different means, he nailed it. He nailed the answer, because this number is almost exactly this number, except there's just one discrepancy in this digit. So he's got 1 where I've got 3. And I really think that this is just a typo. So we should probably contact the editors of the journal and make a correction.
Kevin is also
Oh no, but that's because you see there's a 3 here, that's the 3, and he rounds this. If you round this number at this digit, then the 9 should. Oh, sorry, because you're saying this is yeah, maybe that's an error as well. Yeah, but
it has an approximation. That's his accuracy.
That's right. So this might be a genuine error coming from the fact that he is doing some approximations, but this one just looks like a typo. Right. Okay. So anyway, so that aside, so let's again come back to our ODE. So we're looking for. So we've somehow, using some tricks, we managed to find all solutions, but for x positive. Like that was an important assumption for our trick to make. So what about negative x? So one thing is obvious. If I simply look at my formula for the Euler integral, then the formula doesn't really make sense anymore when x is negative, because this exponential factor, which was previously, in the case when x was positive, was doing this damping at infinity, and that's what was making the integral converge. When x is now negative, the exponent becomes positive and large, and so we had exponential increase at infinity, and so this integral just simply doesn't converge. So getting solutions out of this expression for negative x is not as straightforward. It's not just we have to do something else. And as is always the case, at least from my point of view in mathematics, it always pays off to go complex. So what we're now going to do is we are going to recognize that the real line is just a subset of the complex plane. So now we're going to study. So now now we're expanding our worldview to the complex plane, and in particular, remember the trick. The start of the illegal trick was to recognize that the monomial x was this Laplace transform of the constant function 1. So we can say the same. we can talk about the. We can restate that trick now in complex variables. So so this is a we now understand that this is the Laplace transform of the monomial t, right? And we were the previous definition of this was that we were integrating for along real t from 0 to infinity. So that's just a real ray in this complex plane t, right? And so the cool thing is that the Laplace transform of this, which is what is it? It's just the monomial z squared. Sorry, how do I want to put this? Yeah, let me put it this way. So the point is that now we're looking at values of z for which this integral is actually convergent, right? And what, if you recall, what was making that integral converge was the fact that the exponent was real, large, and very negative. So that was giving us this damping. So now t and z are complex, right? So the size of the exponential is given by the exponent of the real part of what is in the exponent. Sorry, exponential of the real part of the exponent. So we're really just looking at the real part of the ratio between t and z. So imagine, if t is real and positive, and z is real and positive, then the real part of this remains real and positive, and so with a minus we get something that is large and negative. And the fact of the matter is that as long as, if t is real and positive, as long as the real part of z remains in the right half plane, so as long as the real part of z is positive, then the real part of this quotient will remain positive, and so then the exponent will remain very large and negative, and so that will impose convergence on this integral. So, so what I'm trying to say here is that the Laplace transform is well defined. It gives you a well-defined function of z, not just on the real z-axis, but actually in the entire right half plane. Did that make sense? Right. So now if I rotate, now that I'm in the complex plane, I can rotate away from the positive real axis in some arbitrary direction, theta. And I can perform the same analysis. I want this integral to converge. That means that the ratio between t and z, the real part of that ratio, needs to remain positive. And so that means as long as z remains in a half plane bisected by the theta direction, that quotient, the exponent of this exponential will remain real. The real part of it will remain very large and negative. And so this integral will converge. Moreover, so if I now start kind of rotating this ray left and right, what I'm going to do is now I'm going to define a holomorphic function by the same formula, but I'm going to kind of span out or fan out all these half planes, and therefore sweep out kind of a big sector like this. So this is an example of analytic continuation. I started with a function which was defined in a half plane like this, and I start rotating this ray of integration, and I'm comparing, and so I get a new function defined on some new half plane, but in the intersection of these domains, the two definitions agree, and so they define the same holomorphic function. So this is an example of analytic continuation of a function. Does this make sense? Okay, so now let's kind of apply this to our Euler integral. So now this is the same formula with x replaced by z. And now what I'm going to do, the way I'm going to define the complex version of this Euler integral is that I'm going to alter the domain of integration. So I'm calling it gamma z. So in the t-plane, it's just a ray in the direction which is the phase of z. So previously, when z was real and positive, this gamma sub z positive real axis, and then as I start letting z vary in the complex plane, this ray starts traveling. And so this, again, by the same process of analytic continuation, you see that this integral is perfectly well defined for all values of z, as long as I don't take z negative, because that's where this ray coincides with the negative real axis in the t-plane, and that's why we have a problem in the integrand. In the integrand, we have explicitly a pole at t equals to -1, and the domain of integration would intersect that, and so that would break the integral. So as long as we avoid that, as long as we avoid the negative real axis, we get a holomorphic function. So, so what do we do if we do want to understand what's happening with this function for negative z? Well, after all, we are integrating a holomorphic function. So if you recall, let's say Cauchy-Goursat theorem from complex analysis, I can deform my integration contour in a continuous way without altering the result of the integration. So if I take this ray and I start rotating it from above all the way up to, so that it coincides with the negative real axis, as long as I introduce a little deformation of a loop, of a kind of a half loop, so that I avoid the problematic point at t equal to -1, then the result of the integration remains well defined and the same, in fact, right? And the same, and I can do the same operation by rotating the domain of integration kind of clockwise, all the way up to the negative real axis, as long as I introduce a little loop. And so that means now, in order to assign some value to this Euler integral for negative z, there are two choices. I have two choices. I can either integrate from 0 to negative infinity by avoiding this pole at t equal to -1 above or below, right? There's two choices. And they're not the same. They don't produce the same answer, because so we can compute, so that's what I defined these two possibilities as Euler plus minus, just along these two contours. And so we can compare the results of these two integration. What do we get? So if we literally compute this difference, Euler plus, Euler minus. So let's see. So we're integrating the same holomorphic function along the gamma plus contour, going off to infinity, and then coming back and going along the negative gamma minus, right? So the values of our integrand along all these points in Euler plus and, the values of the integrand along all these points, they're all the same. So when I'm doing this part of the integration, I get an overall cancellation. And the same for this interval. The values of the integrand at all these points, they are equal. So when I do integration along this segment and then along this segment in the opposite direction, they just cancel each other out. The only two things that don't cancel are the contributions coming from these half loops, and therefore, what I really have is just the integration of the. I'm just integrating my integrand along a loop surrounding t equal to -1. So this, in other words, all I'm doing is I'm computing the residue of this meromorphic function at t equal to -1. It's literally the residue. So what is the residue of this function? Well, how do you do this? You remove, you remove the denominator, and you just plug in t equal to -1, where you're computing the residue. What do you get? So there's a 2 pi I factor as usual, and you just get, you just get 2 pi I times e to the 1 over z. That's the residue. So, so the important observation is that although we started with one formal power series, that's the Euler series, we came up with a method which is it's a consistent method. The method works the same way for all directions. It lifts this formal power series to this analytic function, which was the Euler integral. But the method has kind of problematic directions. So in this case, the problematic direction was the negative y-axis. And whenever you encounter this problematic direction, you observe a discrepancy in the output of this algorithmic method, which is the Borel summation. So if you resolve that difficulty, which was, in our case was a pole, if you resolve it one way, you get one answer, Euler plus, and if you resolve it another way, you get another answer, which was Euler minus. And those two ways of resolving this difficulty, they do not agree. There is a discrepancy of, an entire function, 2 pi I e to the 1 over z. And so this really is kind of the basis of the Stokes phenomenon. So you should think that we have one formal object, an asymptotic power series, and we're lifting this asymptotic power series to an analytic solution using some method. And the method kind of, in certain directions, has ambiguity. And across those ambiguous directions, we have a jump in the output of the method. And it's a discontinuous jump. And so this is kind of the basis of the Stokes phenomenon. What else do I want to say? Skip this. Yeah, okay, so maybe I'll end my slides here. What are we doing with time? Oh, perfect. So I want to return to my concrete example briefly, and then I think we'll all be ready to go home. Right. Okay. Okay, so let me just rewrite this this result that we found. So we have this formula. So I can state it like this. So given a direction theta, as long as it's not x minus prime, and a sector u theta containing theta. So let's imagine this is my z plane, and so here's my origin, and I'm giving this direction theta, and let's say some kind of sector like this. Let's say this is my u theta. The point is that this expression, let me call it star, this expression consistently defines for me in this sector a holomorphic function of z using that formula. Simply by taking the initial direction theta and just rotating it through all the possible directions in that sector. So star defines a holomorphic function for G theta of Z on Q theta. So maybe I can draw an image. What I mean is that in the t-plane, you kind of, so there is this whole of -1. And then so we start with this direction r sub theta, right? And then we just sweep out the rest of the directions. Using rays, except that we're being very careful because if I want a ray pointing in this direction, I need to recognize that it's one which I obtain by rotating this ray. So it really looks like Does that make sense? So this is a pictorial description of how I'm defining this G theta. So the upshot of this is that in this sector U theta, we get a gauge transformation. G theta of Z, which is literally just, I take this holomorphic function G theta, and put it in the formula for the big G. So and it has the property such that G theta actually admits this formal gauge transformation that we've constructed earlier as its asymptotic expansion. And so in particular, that means we get a fundamental solution y theta, which is just G theta applied to the fundamental solution of the normal form. We can even, I can even write explicitly what this is. It's like 1 over z, e to the 1 over z, 0, G theta 1. And this is well defined on this sector U theta. Does this make sense?
What about the origin?
Yes, exactly. What about the origin? So this sector U theta, it's an open sector. It does not contain the origin. It does not contain the origin. And it also, remember we were talking about this infinitesimal disk? So U theta is not a neighborhood of 0. So it does not belong to the, it's not, it does not represent the infinitesimal disk. It is genuinely a different type of neighborhood of the origin. It's a sectorial neighborhood of the origin. Let me write this word. It's a sectorial neighborhood of the origin. What this should kind of trigger in your mind is that if we're studying these objects, if we're studying systems with irregular singularities, the analysis that we've made so far, which is to say that there are no gauge transformations, which are holomorphic at 0, which can put my system into some normal form. The only thing I can get is something that is defined in a sector. So that means these phenomena, they're dictating to me that I need to expand my worldview of what I mean by local geometry near a point. It's not enough to just consider disks of arbitrary small radius, I need to have access to more sophisticated neighborhoods of the origin. In particular, these type of sectorial neighborhoods seem to be playing the fundamental role. So, now what I will do is cover the neighborhood of the origin. Maybe the punctured neighborhood of the origin. With two sectors. So let me draw a picture. So here is my origin. And let's say, so one sector looks like this, and let's say, it's somehow bisected by the positive imaginary axis. Like this, let me call it U plus, and then another sector which is bisected by the negative imaginary axis. Let me call it U minus. So by that argument, I have two sectors with a kind of selected direction. So I get two solutions of the Euler equations. Euler equation on U plus minus, and so that gives me two gauge transformations on the two sectors, and therefore two solutions, two fundamental solutions. Does this make sense so far? So let me compare these solutions. Right, I have two sectors, two open neighborhoods. They're intersecting. Each one comes naturally now equipped with a fundamental solution. Are they the same fundamental solution? Or what's the difference? How do they differ? So let's compare them. Let's compare these fundamental solutions over the subset where they're both defined. So that over the double intersection. What is the double intersection? Let's draw it. I just intersect these things. Origin. So the double intersection of these, just these two cones, they're disconnected, right? Because of course the origin does not belong to any of these. So they're disconnected. Let me call them maybe W minus and W plus. So this thing is the union of W minus, disconnected union of W plus. And so here's what we can observe. So let's observe the following thing. So over the is that a question? Over the W plus, just because of the way we've defined G using those rays, which point the same direction as the phase of Z in this region, the definition of G plus and G minus, they just agree. So G plus of Z is equal to G minus of Z for all Z in W plus. And so that means that the gauge transformations G plus G minus over this double intersection W plus, they agree. And that means the fundamental solutions agree as well. So there's no discrepancy there. However, if we look at the other double intersection, the other component of the double intersection, then that's where the definition of G encounters that pole at t equals to -1. And so that's where we see a discrepancy. So, but if Z belongs to W minus, this is now a difference between swinging this ray of definition, from above or from below. And we saw that there was the difference between the two. I hope I got the signs right. The difference was this 2 pi I multiple of e to the 1 over z. So that means that my fundamental solutions are different. So I can compare them like this, let's say, just compute 0, sorry, not 0, plus, or maybe minus, sorry, let me compute it like this. So the ratio between y plus and y minus, compute it like this. So how are these defined? They are defined by inserting G0, sorry, G minus, and here inserting G plus, Y0, right? So this thing is e to the minus 1 over z, 1, 0, 0, minus G minus, 0, 1, 1, G plus, and then finally e to the 1 over z, 0, 0, 1. So if you compute this guy, this thing, of course, is just, they're unipotent upper triangular matrices, so in a multiplier I just add the off-diagonal terms. 1, 0, 0, 1. And so over here we just have this difference that we difference that sort of basically encodes the Stokes phenomenon. And so you can conclude maybe by saying that the discrepancy between the two fundamental solutions depends on which component of the double intersection I'm looking at. And so if I'm looking at Z in W minus or Z in W plus, so Z in W plus, the discrepancy was none, it was just the identity, they were equal. But in W minus, we get a genuinely non-trivial ratio of these solutions. So maybe I'll call these matrices, suggestively, call them S minus and S plus. So these matrices are kind of, they're famous matrices. So you could say, maybe another way of writing this is that y plus is the same as y minus with s minus matrix relating them. So this is on W minus. And on the other end, y plus is the same as y minus.
But that's not the right ordering because we define it as y minus inverse, so it should go on the other side.
Y.
No, my bad.
No, I think this is okay.
I confused myself.
Yeah,
Sorry.
that's okay. I always confuse myself with this as well. So right. Okay. So these matrices, S plus S minus, they are called Stokes matrices. Very sort of famous object in mathematical physics. And so the final thought that I'll finish on is that this is now we've sort of entered very deep theory at absolutely safe to say at the kind of cutting edge of current research. Lots of people study this at the moment, including yours truly, which is that, you know, so we kind of try to encode these moduli spaces like the ones we've been considering, or their analogues in more sophisticated, more general situations. These moduli spaces, by the way, let me give them a name which you may see in the literature. They're called de Rham moduli spaces. The things that we've been discussing, they are examples of kind of a much wider subject of de Rham moduli spaces. And so the theory is to encode these moduli spaces in terms of normal forms, like what we've been doing. And with the addition of what is called Stokes data, which is just collections of Stokes matrices appropriately assigned. So you could say that, if you remember that intermediate, I wrote a moduli space where the gauge group was analytic gauge calculations, and I said that that was too big. It was too big for us to kind of make sense of. And then down there, I introduced the same type of moduli space, but the gauge group was this much bigger gauge group of formal gauge transformations, and I said that that was too small. It's killing too many invariants that you could associate with a particular system to distinguish one system from another. And so the thing that should sit in the middle is basically some kind of space which encodes normal forms, exactly of the type that I described. Like these, you just take the principal part and just look at kind of the diagonal part of the principal part, so to speak. But then you need to add to your encoding mechanism, you need to encode this Stokes data, which is how you construct the, or like which Stokes matrix you take, how many, what properties they must have, how do they combine. So this is kind of part of much bigger and beautiful story. Okay, so I'll finish here. Thank you everyone so much for coming to this school. It was a lot of fun.